Hey there, everybody. Welcome back. We are doing multiple integrals, double integrals over a region that is better in polar coordinates. These are some examples. Let's just jump right into it. We'll have two examples in this video. The first is find the volume of the solid bounded by the paraboloid z equals 9 minus x squared minus y squared and the xy plane. So z equals 0. So we got a picture of what that looks like right here. It's a paraboloid opening downward, and we're stopping at the xy plane. An overhead view looks like this. Okay. So we're doing, and you'll see if we have x is 0 and y is, well, if we have x equals 0 and z equals 0, y has to equal 3. If we have z equals 0 and y equals 0, x has to equal 3. So it's a circle with radius 3, and it's doing the whole thing. So 0 to 2 pi. We have our z equals 9 minus, I factored the x squared plus y squared out of the negative, so that I can rewrite it as 9 minus r squared. So we're going to set up our integral. We already determined the limits of integration were 0 to 3 and 0 to 2 pi. My function is now in terms of radius. And I don't forget r dr d theta. Got to have that r in there. So I multiply the rn, and I've got 9r minus r cubed is the function we're integrating with a dr d theta. We go through, we can chug along through it. So when we integrate it, we got 9 halves r squared minus 1/4 r to the 4th. Evaluating from 3 to 0 or 0 to 3. You'll see that just ends up being 81 over 4 inside there. And then we integrate for theta. We got 81 over 4 theta. From 0 to 2 pi is just 81 over 2 times pi. Another option you have is once you have it down to you've multiplied the Rn, this is now a separable function because the limits of integration do not include the other ones. So we're going to do 0 to 2 pi for d theta and 0 to 3 for 9r minus r cubed dr. And 0 to 2 pi for theta is just 2 pi. And we already showed this part up here was 81 over 4. So you get 81 pi over 2. Okay. Let's take a look at another problem. We're going to let the function z equal xy plus 10. And we want to find the volume of the region below z and above the annulus. 2 is less than r less than 4, and theta is between 0 and 2 pi. And annulus is just a region between two concentric rings. These are terrible rings. So z's in terms of x, y, we got to make our replacements. Don't forget x is r cosine theta and y is r sine theta. So when we plug it in, our function becomes r squared cosine theta sine theta plus 10. And since sine 2 theta equals 2 sine theta cosine theta, I divide both sides by 2 and I get 1/2 sine 2 theta equals sine theta cosine theta, and I made that substitution in, replacing cosine and sine with sine 2 theta with a 1/2. So we plug it into our integral. It is not separable now because we've got a plus sign in there. So we need to just do as is. So I multiplied the Rn and we integrate with r. We've got 1/8 r to the 4th sine 2 theta plus 5r squared. Evaluating from r equals 2 to r equals 4. I did not clean anything up. I just plugged it in. I got 32 sine 2 theta minus 2 sine 2 theta plus 80 minus 20. When we clean that up, we get 30 sine 2 theta plus 60. We're integrating from 0 to 2 pi. I did a little quick u sub just to make sure I didn't screw anything up. So u equals 2 theta, du is 2d theta. So I got a 1/2 du equals d theta. I just multiply the 1/2 in. I've got 30 times 1/2 is 15. and then 1/2 times 60 is 30. And that's our du. So I'm switching to du. To do that, I got to change the limits of integration. When theta equals 0, u equals 0. And when theta equals, wow, that should say 2 pi, not 2u. When theta equals 2 pi, we're plugging it in, we get 4 pi. So my new limit is 0 to 4 pi. We go ahead and solve that, or integrate that. Negative 15 cosine u plus 30u from 0 to 4 pi. We see that we get 120 pi. That's it for this video. Peace.